second squared, so that gives us a square root of a kilogram meter per second squared over meter kilograms.
So the kilograms cancel out with meters. Seconds squared?
Almost.
Just seconds.
Still almost.
Radians per second. Or what?
Closer.
1 divided by seconds.
Don't forget we're taking the square root.
Radians?
1 over
Yeah.
second.
Okay. Look, I don't know if you heard what Ali said. The kilograms cancel, the meters cancel. Second squared is still on the bottom. It's not square root, so it's square root of 1 over second squared, which is 1 over seconds. Now, 1 over seconds is an odd unit. It is not wrong. However, for clarity's sake, you generally stick the radian in there. So it's radians per second. Remember, omega is the same symbol we use for angular speed. Has the same units. If only all physics worked that nicely. So 1.806 radians per second. So my speed when it passes by this point right here. And I know that's where the maximum speed is because as I pull it down, the spring is pulling up until it reaches the equilibrium spot. At that point, the spring equals the weight. And then once I get past that, the spring is now pushing downwards. So the spring is in the same direction as motion. The net force is in the same direction as the motion, so it's speeding up until it gets to here, at which point it balances out, and then the net force is downwards. So we get from this, there's my maximum speed right there, it's just the amplitude. Think about a graph, the largest it's going to get is the amplitude. So Vmax, which is at that spot right there, is 5 meters. That's my amplitude, times omega, 1.806 radians per second. Meters per second.
Yeah.
Starting with units.
9.03 meters per second.
One way, one, up. While we're here, let's figure out what the maximum acceleration is. A max, well again, it's just, there's my amplitude, that's the largest value that A can be, is going to be 5 meters times 1.806 radians per second squared. Hopefully somewhere around there.
No. I think we've seen.
Or, you didn't get that?
I didn't get that. I got 16.31.
16.31?
Yeah.
Do we have a mistake over there?
Yeah, I got 16.308.
Here,
Yes.
and before?
The 13.06.
Is my memory off? Because when we solved it over here,
No, the number I got originally was 13.06. But that number, are you saying that's probably wrong? Because they should be the same thing?
yeah, they should be. So when we did it before, we had that when it was stretched the most, so since weight is involved here, it was stretched 8 meters. So K was 13.06.
Yes.
Yeah.
Okay, not acceleration. Did we solve for acceleration? What do we get?
16.3.
16.32.
Okay, so we did get the same thing. All right, sorry. It's only gonna get worse as you get older. All right. So we found acceleration two different ways. We found the maximum speed one way. So of course, let's find maximum speed another way. Questions before I erase stuff?
I'm assuming this is gonna develop just as, momentum, and how you have like 3 methods or so, or like 2 or 3 methods, and you just pick one and stick with it. Or no.
A little less, but generally I don't specify the method to pick here, so in that sense, yes, it is similar to the momentum bit. All right, so again, accepting that maximum speed is passing through this point right here, let's do it by energy. So I've got, I know that the three forces, or the two forces involved here, the perfect spring or ideal elastic force and gravitational force are both conservative forces. There are no non-conservative forces involved, so energy is conserved. And that's just kinetic. The question's gonna come up in just a moment, so prepare yourselves. K initial plus U initial.
How do you, I don't know if this actually works, but how do you distinguish the kinetic energy from spring constant? Because they're both big K.
Oh, spring constant is supposed to be a little k.
Because they're so different.
Yes, very much so. Like the big P and little p, you should be able to tell the difference when I write on the board.
I have seen one professor, he does like the K with the loop on, like.
Yeah, I sometimes do that. Apparently I'm just getting sloppy. And then there's the K in kilo for kilogram.
And why is spring constant not a C
Why is it not
first?
a C for constant?
Yeah.
K for constant.
Or,
If in doubt, it's from the German, Latin, or Greek.
we can blame that.
That's right. Occasionally the French. Like M for slow. Really? Come on. K final plus U final. All right, we have two conservative forces. So what does that tell us about the next line of my equation here?
We are,
Can you say that one more time?
There are two conservative forces in play, gravitational force and the elastic, ideal elastic.
So energy's gonna be conserved.
Okay, that helps us here. What is, if the fact that there's two conservative forces, how does that affect this?
we need to add another set of equations. Meaning,
Do you want to narrow that down?
K1 plus U1 plus K1 plus U1.
You have two kinetic energies?
Well, we have two conservative forces.
Yes, but conservative forces have nothing to do with kinetic energy.
Lovely.
But do they have something to do with? Other people can chime in, cut Ibrahim off before he gives the answer. Make yourselves appear brilliant.
Indeed, so. It's not coming anytime soon.
You did K1 plus U1 plus K2 plus U2,
Yeah.
and I said, why are there two kinetic energies?
Yes.
And I said, conservative forces have nothing to do with kinetic energy.
Oh. Add a potential energy.
There are two potential energies. Every conservative force has a potential energy formula. So this becomes K I plus UI for gravitational plus UI from spring, and then U final gravitational plus U final spring. All right. I'm about to ask that question. What's the formula for kinetic energy?
1/2 mv squared.
It's like a funeral dirge.
That's what we were going for.
Potential energy, gravitational potential energy.
MGH. Or really, which one are you asking for? What?
I just mentioned gravitational.
Oh, you said-
The elastic, the ideal elastic potential energy.
1/2 K. Or
You stop before you finish.
1/2 KX squared.
There we go. Technically delta x. But on textbooks, we'll just drop the delta. 1/2, and then the same thing, but final. Plus MGH final, plus 1/2 K delta x final squared. All right. So we're just writing down all potential energy, all the energy formulas again is equal to the same thing, final. And now, what is zero?
Well, we said equilibrium at. We're still going with 2, like up there, or is that gonna affect?
Which way do you wanna do it? You wanna do that equilibrium is in that middle spot?
Sure.
X is equal to 0 there?
Yeah.
Okay, we'll solve it with x is equal to 0 there.
Where is there?
So Ibrahim wants to solve it with x is equal to 0 here.
Okay.
Any objections? Okay.
All right, so right off the bat, if you're choosing x is equal to be 0 here instead of here,
You can get rid of, gravitational.
yes. That goes away and that goes away because of how Ibrahim, not because he said so, but because how Ibrahim set up the problem. So by doing that, we are establishing x equals 0 at, yes, delta x equals 0 at the 4 kilogram equilibrium location. And for those who are fans of gravitational potential energy, we'll solve it again with that in place, just to ensure that we get the same answer, unless I forget and think that we come up with a different answer.
Could we also cancel out delta x's if we're at 0?
With delta x what?
Just delta x's, because if we're starting at 0, I don't think we're moving.
No, what he was establishing is x equals 0 here,
Alright.
not that we're looking at only this problem. We're still looking at this problem, just we're defining
Okay.
our locations. However, we do have 2 more things that we can cancel out. 2 terms. Sorry.
Initial velocity? Because in this problem, it's just, we pull it down and then we just let go.
Okay, yes, but I'm gonna nitpick some of the language there, although what you said is not technically wrong. However, there is better wording, not the initial velocity,
Initial kinetic energy.
which is dependent upon, not the
The
velocity.
initial
Potential energy?
What'd you say?
speed.
Speed.
Oh, it's not.
No vector symbol here, it's speed.
Credit.
Okay. All right, because the initial speed is 0. All right, anything else we can get rid of? Well, yes, because I said earlier there were 2 things.
Would it be final speed or no?
I hope not, we're trying to find the maximum speed.
Okay.
Would it be, the final spring constant?
Wording,
Because, because displacement is 0.
right, but you wanted to cancel out the final spring constant.
Oh,
That's what I heard you say. That's why I said wording.
sorry. I can't remember words.
Anyone wanna help him out, or just let him flounder?
Flounder is good fish.
They're gonna okay. You're gonna cancel out, or this is equal to 0, this is the final elastic potential energy, spring of potential energy. I was redundant there, final elastic potential energy. For the reason that he said, it's because delta x is equal to 0 there. So what we're left with in this is 1/2 k delta x initial squared is equal to 1/2 mv final squared. That's what it boils down to. At this point, we can get rid of the 1/2s. And what we're left with is that my final speed, or my maximum speed, because of where I chose the final position to be, is equal to k over m square root times delta x, the initial. Recognize delta x initial. That's how far I stretch it off of that equilibrium. That is the amplitude. Square root of k over m, that's just the angular frequency. This is omega times the amplitude.
Isn't that our equation?
That's what we got from over here.
Right, the A times omega.
Yeah.
Now, when we say like sine and cosine, are we like when we're doing that in the calculator, for example, are we gonna put that in there? Or no?
All I wanted was the maximum speed, so I don't need this part
Oh,
yet.
yeah. And
Don't
then-
worry, we'll do some of that.
A little bit of a trick.
Right, the teaser. All right, so let's solve it one more time, because I know you love this problem, so let's do it a third time. This time we're not gonna get rid of MGH. So we're gonna choose x is equal to 0 where it is in the first spot. Jack?
2 questions. F is relating to that, is it easier just to choose it so we can ignore the gravitational force?
I would personally, yes,
Okay.
but like most things in physics, it's how your brain is working at the time you have to use it.
And then all of this, justifying that, is this just showing us how that equation works?
Yeah, or showing that multiple approaches get to the same spot.
Okay.
All right, so
Should we plug in numbers, we'll still get the same thing we got here.
yeah. I can do it with all letters, show that we end up with this again. If you prefer that,
Oh, okay.
None.
you want numbers. Go any questions about the part of just a reason. All right, so we are back to here. We still got rid of that one over there because it still starts at rest. And all right, so we have x is equal to 0 here. And because we're choosing this spot, we have to include weight and more specifically, the gravitational potential energy. All right, so we now have to decide upon our gravitational potential energy. Where's h equal to 0?
At the maximum.
At the maximum what? Maximum speed, maximum just pull here. All right, Ibrahim Sway first. H equals 0 here. Because he said so. So this is 0.
That's zero because Ibrahim said so.
Wouldn't it be fine?
Like, that's where we pull it when we let go. If you went at final, then we would make this h is equal to 0.
So the equation that we're doing is from the bottom,
We pull it down to here and let go.
let go, and then the equation starts.
Yes.
Okay.
Oh. All right, so, oh, that's 0. All right. Well, it's definitely moving. It had height h is in 0, delta x is in 0, delta x is in 0. All right. We simplified as much as we can. So I have this 1/2 times 13.06 repeating times my initial displacement or initial off of equilibrium, which would be 8 squared, is equal to 1/2 times my mass times my final speed. And again, it does require, at least the way we're doing this, you can't set up a general equation for velocity or for speed, my apologies, for speed. Take the derivative with respect to time, set it equal to 0, and solve it that way for those who've had calculus. But acknowledging that the fastest speed is going to be at this point right here, then that's what we're trying to find. So v squared plus 4 times 9.8 times my height, which would be 5 meters, plus 1/2 times 13.06 times delta x, which at that point will be 3. Take a moment just to make sure you understand what each of these numbers from where. Saved. The moment to make sure you understand where each of the numbers comes from. Or from where each of the numbers comes.
The 4 is just the mass. Where did we get the 13.06 from?
Spring constant.
Okay. Just for the